Well, welcome to the coding tutorial for your VEX training. This tutorial will just cover the very basics of getting your board moving, your drivetrain, and yeah, okay, so let's dive right in. There are 3 IDEs you can use to code VEX, and let me explain like the pros and cons of each. So the first one is VEX Code Pro V5, which is the application made just for VEX. But honestly, it's really bad. It will crash all the time, and it hogs a lot of your memory. So honestly, like the other options are a lot better than this. So just choose something else. Well, the second option is the Visual Studio Code extension. So this one is actually pretty good. It's pretty good. The major pro of this one is that it enables you to use some templates like the jar template. But if you're really unlucky and your Mac is set up a bit weird, it can be very annoying to set up. So, but honestly, it's quite rare for that to happen. So if you already use Visual Studio, this is a pretty good option. Yeah. The last one is VEX Code V5, which is the web-based version. This one, and honestly, it's absolutely a good choice. Even though it's web, I know it sounds a bit cringe, but honestly, it's quite good. It doesn't crash a lot, and they've polished the website quite a bit recently. So the world's board was coded entirely in web. Okay. But there are some cons, like you can't upload from your controller. You have to connect directly to the brain, and there's some clunky stuff. And the biggest one is that you always need Wi-Fi to access your code, which might be an issue. But honestly, if you have hotspot, it's not too bad. So if you're new to coding and you just wanna get started now, the website, you can use the website. So in this tutorial, we'll use the website. When you just enter the website, the links here, codv5.vex.com. It looks like this. Okay. So we don't want to use blocks. If you code in blocks, it'll be very messy and long, and it's not too hard to code in text anyway. So let's get a text project. We'll use Python in this one. It's just easier to read. Okay. I'll go through the UI of the website. Okay. So when you create a new file, it's called VEX Code Project by default, but you probably want to change the name. So I'm gonna change it to my board code or something like that. Okay, so this name is what will appear on your Brain Hub screen. Okay, so whatever you put here is the name of your program on the Brain Hub. You can press save and keep it somewhere nice. Okay, and it will be saved. So in the folder I just saved it in, you can see my board code. Well, and then this is the slot. So in your brain you have 8 slots where you can put different programs. If you choose, you can choose 2, 3, but the thing is, if there's already a program in one and you choose one and then you upload it, you will replace the program at 1, so you lose that program. So just choose a slot and keep to it. Okay. Yeah, that's how you save a file and rename your file. Okay. You can share this V5 file with your friends and stuff. And if you have a file and you want to open it, just go to File, Open, find it, just click, and yeah, it will open right up. Okay, as you can see, it's a different file. Let's go back to that file, my board code. Yeah, so that's how you open, close, and save files. Well, okay, so how do you connect the brain to the V5 website? Over here you can see there's an icon, brain. Just click it, connect, continue. I don't have a brain on me right now, but if you do it, make sure the brain is plugged in to the battery, turned on, and connected to your laptop directly, not through your control or anything. Okay, so like this setup lah. When you click connect, and in this screen you'll see this. Okay, and you'll see 2 port comes up. You want to select the port with the lowest ID number. So you see 14201. That's the one you want to select instead of 14203. The second port for this is actually like a port for you to send print messages to the console over here. But we won't cover that in this tutorial. You can read online if you're curious about it. It's pretty useful. Yeah, so you just select the lower one, and yeah, you're connected. If you want to download code, okay, you verify whether your project is there any errors first with the build button. It takes a while because it's a website. And then if you're connected to a brain, the build button will turn into a download button. You just click it and then it will download, and then you'll see the program pop up on your brain. Yeah, so that's it. Okay, what else? Okay, so let's start coding. So you see over here this little button, let's click it. So this one my not favorite lah. It's a pretty nice feature to have. You can add devices like your motors and controllers over here. So if we look at a board, this will be our sample board. Okay, you can see what do we have here. We have 4 motors and a controller, right? So we just need to declare 4 motors and a controller. Let's do the controller first, and done. And if you have a keen eye, look at these numbers, alright? Kind of change, drop 1 line, right? So what's exactly happening here is that even though it doesn't look like much, every time you create a new text file, the website generates this boiler code for you automatically. You shouldn't touch anything here. If you do, you'll mess up a lot of things. So just don't touch anything here. But I just want to show you what happens. Okay. So when you add a device, bang. What they're doing is actually adding this line of code over here. Okay. So this line of code is the one that declares your device. If you were to write this code, if you were to not declare this in here and write the declaration in your own project code, it will absolutely work. Okay, it's absolutely fine. But honestly, why would you do that? Because when you it's just cleaner to do it here. And another plus is on the left here, you see this is your API. Okay, this is your API reference. You can find suitable functions that you want to use here. But if you notice, there is no motion, there's no motion blocks, which is kind of weird. How do you move the board if there's no motion? The reason there is no motion is because you didn't add the relevant device. So if I add a motor here real quick, bang, you see the motion block or motion section, it pops up and all my motor related function comes up. And it's not just the motors, okay? For example, if I add a inertial sensor, you see no additional section pops out. But if I go to sensing, and bang, you see I have new inertial functions to deal with. So if you're trying to find a function and it's not there, you probably just haven't added your devices. And you should add your devices at the start before coding anyway. Yeah. So let's actually do the example. We have 1 controller and 4 motors. Let's add the controller first, because it's the most simple. Bang, I have my controller ready. Okay, for the motor, let's say I'm at port 1. Choose your actual port. Okay, what should we name it? You shouldn't name it 1, 2, 3, 4. It'll get really messy really quick. So choose a proper naming convention and stick to it. The one that is standard is to say what direction kinda is facing. So if we say this board and this is the front, so this is the left side, right? This motor will be on the front left side of the board. So and then this one will be this one will be back left, this one back right, and this one front right. So that's a normal naming convention. Okay. And furthermore, because all these motors are drivetrain motors, you normally want to denote that first. So I'll go drive, and say we're declaring this one front left. Actually, normally I prefer going by the side first, because honestly the side is more important than the position front or back of your motor. So normally you go by the side, but it's really up to you. It doesn't really matter. Front, left, front. Yeah. Okay. So naming convention, just keep it consistent. That's the only important thing. Okay. Then you choose your cartridge of your motor. Remember the front is a cartridge. Hold on. Where is it? Okay, never mind. Here. Yeah, the cartridge color. Just choose it. Okay. This is honestly the only issue some people have, whether to reverse the motor or not. So if you see I press reverse, right, the direction in which forward is flips lah. So during the normal phase it turns that way. If you reverse it, forward will be like that. To make things easy, want to make sure that forward always turns all the wheels forward and moving forward. So how do you check that? If you see the motor, you'll see this direction thing. On this motor it's clockwise, but some motors are counterclockwise, and depending on how you install them, it might change. So on this very specific example, it's clockwise. And let's just look at the example of this motor. okay, the left back motor. So imagine that this is what it looks like, okay, and say, how do you check whether to reverse it? You imagine that you're pushing the board forward to the front, okay, and then you think, which direction does this wheel turn? If the board is moving to the front, the wheel must be turning clockwise, right? So it turns clockwise, and let's see what direction this motor is default to, clockwise as well. So if the wheel and the direction of your motor is the same, you don't have to reverse it, you can keep it as normal. However, say for example this arrow was the other way around and it was anti-clockwise, but this wheel was clockwise, then you have to reverse it. Very simple, okay, but every single motor might have a different configuration. So every time you declare a motor, you have to check, okay. So this is where most people mess up. If your code is not working, it's probably this. So check this very carefully. Yeah, let's just move on. I named it wrong. Sorry, front, left, front, and you just do this for all 4 motors. I'm gonna move forward a little. Right. And I'm gonna assume all of them are like not reversed, okay. But you shouldn't assume. You should check. Right. Yeah, keep your punctuation consistent and everything. Okay, so I've declared all my motors. What next? Well, maybe before we move on, we try and figure out how do you move the motor in the first place. So if you have a question like this, how do I move a motor, how do I read a sensor, run to the API. The API is here to help. Okay, so while we have motor problems, which one should we look at? Probably the motion tab, right? So let's read it. Motor.spin. Wow, I don't know what that means. What should I do? You just check here and read it up. Commands that spins a motor forever until a new motion command is used. Okay, so it looks like every time we want it to do something new, we have to call this command. Okay, that's cool. We should keep this in mind. Oh wow, set velocity. So that's like setting our speed, right? Let's just look. Sets the speed. Yep, exactly. That's exactly what we are trying to find. So maybe as an example, turn on motor. We're gonna try turn on motor. Yeah, let's read it. It accepts velocity and then units, and it accepts a range of 100, -100 to 100%. Okay, as a tip, don't use the RPM. It's a bit convoluted if you set it up wrong, and then it's very hard to debug. So just use your percentage. Okay, it's a lot easier anyway. So let's set our velocity. Let's just do one motor. Drive. Set velocity. Let's say we want to set it max speed. You can set it to negative. It will just mean your motor will go backwards instead of forwards. Okay. So and then once we set our velocity, it doesn't start moving. This just means what speed it should go at when it. This just means we told it what speed it should go at when we tell it to start moving. But we haven't told it to start moving. To do that, we have to add dot spin. Okay. So how do we stop the motor? Well, there's a function here, very convenient, called stop. That works perfectly fine. But this also works fine. You can do this thing, but just set it to 0. Both work fine. Stop is shorter. Just pick whatever you want to do. Okay. Well, we figured out how to move a motor, but that doesn't really help because we're trying to control the motor with control the board with the controller, right? So, how exactly do we translate controller commands to movements for 4 different motors? Well, when you have a problem code-wise, you should like follow like a process, you know, like find test cases which you know the answer to, and then you try and make observations and stuff that relates the test case to your answer, and see whether you can generalize and find a solution. So yeah, so I'll go through the process of how to find like the solution to how to write the code. But if you just want a code, you can skip ahead to this timestamp over on the screen. Yeah, okay. So first find test cases which we know the answer. So we can just start with something simple. Okay, maybe before that, let me explain how the controller works. So you can see there's 4 axes. This is axis 3, axis 4, axis 2, axis 1. I don't know why they numbered it like that, but that's just how it is. We are currently going to do an arcade drive, which is what most people in this club uses. Basically, we only use axis 3 and axis 1. Axis 3 determines your forward and backwards movement, or axis 1 determines your left and right turning. Yeah. So let's see. Say we just want to move forward. What will we do? We'll push this joystick all the way up. What value will axis 3 return us? That will return us 100, right? Because it's all the way up. So it will return us 100. So when we move forward, what speed do each of these motors move at? All of the wheels are spinning this way, correct? That means all 4 motors are spinning forward, say arbitrarily at 100% speed. So we can say that for this test case, the left motors and the right motors both move forward at 100% speed. Fair enough? Okay. Second test case, so we move backwards. This means axis 3 will give us negative 100, right? And here, if we move backwards, the wheels will spin the other way, correct? Which means all 4 wheels will spin at negative 100% speed. Well, next we need to, make some observations. What can we see here? You can see all these numbers in this test case are the same. And so is this test case, all negative 100. So we can kind of generalize for moving forward and backwards that the left speed should be equal to axis 3, sorry. And so should the right stick. Is this fair enough? Fair enough? Okay. So let's move on to this stick. Okay, just now we talked about this stick. Now let's move on to the turning stick. Say we are turning right. So we push the joystick to the right. What value will axis 1 give us? It will give us 100, right? Okay. While we are turning to the right, let's look at our robot. If we are turning to the right, this way, right? Turning to right, this way. We will expect these 2 motors to move forward, right? While these 2 motors will move backwards, like a spot turn in Lego. It's the same concept. So when we are turning right, our left side motors will move forward, while our right side motors will move backwards. Let's just write that down. Our left side motors will move forward, our right side motors will move backwards. Okay, fair enough. Say we're moving, okay, new test case, okay. Now we're moving to the left. What value is axis 1? Negative 100 versus 1. Here, right? Let's go back. Now we're turning to the left, so that way. Okay, towards the left, that way. What do we expect? The right side motors to move forward and the left side motors to move backwards, like the spot turn. So let's just write it down. Left side motors will move backwards, right side move forward. Well, any observations here? Well, we can see that axis 1 and the left, the values are the same. Here 100 and 100, negative 100. But on the other hand, the right, the value of the right is the inverse, or like the negative of axis 1. So when it's 100, it's negative 100. When it's negative 100, it's 100. So if we generalize, the left side will be equals to axis 1. But the right side is negative axis 1. Okay, well, we have generalizations for the left joystick and the right joystick. But how do we combine them? Maybe we could combine, just add them up. Let's just add them up and see what happens. So the left, we have 2 equations here. Left equals to axis 1, left equals to axis 3. What happens if we add them up? Left equals to axis 1 plus axis 3. And let's add up the right one. Right equals to axis 1 and right equals to negative axis. Oh, sorry, right equals to axis 3 and right equals to negative axis 1. Right equals to axis 3 and negative axis. Let me just flip this so it's easier to read. Okay, well, how do we validate whether this is a correct solution? We can just plug in numbers and test whether they make sense or not. So, say we're both pushing the left stick forward and the turning stick to the right. We can kind of guess that it might be like a pivot turn kind of movement. Definitely not a spot turn, but definitely not moving forward either. So maybe a in-between kind of turn. So let's see what happens, okay? If we move axis 3 forward, it's 100. Axis 1 is also 100. Let's see what our result is. Left is 100 plus 100 is 200. But if you remember this, it only accepts until 100%. So when you feed in 200 to this function, it will just cut it off until 100. Whereas for the right, 100 minus 100 is 0. So let's see, the left side is moving at 100 and the right side is moving at 0. If the left side is moving forward but the right side stays still, isn't that a pivot turn from Lego? So it fits our hypothesis. It's kind of an in-between from moving forward and a spot turn. So yeah, this looks correct. Maybe we try another test case, okay? Maybe if we reduce the amount we move forward by, let's say until 50, we would expect more of a tighter turn, right? Because there's more turning than moving forward than just now, which was 100, 100. So it should be a tighter turn than a pivot turn. So let's recalculate everything and see what we get. Left, 100 plus 50, 150 is still chopped off to 100. As for the right, x3 minus x1, 50 minus 100 is negative 50. Negative 50. So let's see, the left is moving forward at 100 and the right at negative 50. And look at that, the left is moving at full speed and the right side is moving backwards but only at half speed. So it's turning more than a pivot turn but not as much as a spot turn, which is exactly what we expected. So we validated that this is a correct formula to have, and we can code this in now. So this is like if you have problems trying to find like ways to control your board, this is how the process should look like for you. Okay, code now. Time to code. We have the formula now, we just have to put it into machine speak for the robot. So shouldn't be too hard. Okay, let's say we want to driver control code. So what do we need? First, we need the values of axis 3 and axis 1, right, from the controller. Again, how do we do that? I don't really know. Let's just like look through the API. I can kind of guess that it might be around sensing. Oh, look at that. Controller.axis1.position. And it returns a range of 100 to negative 100. Yeah, exactly what we need. So for simplicity's sake, I'm just gonna call if you think about it, right, axis 3 kind of represents the forward movements of the robot and axis 1 kind of represents sideways. So for readability, I'm gonna name them as such. Okay, so forward is the exit controller axis 3 dot, okay, and sideways controller dot. So now we have our two axis values. Perfect. We just need to write this formula down. We just need to write this formula down. So for simplicity, I'm gonna call left train. I'm gonna call my left value left train. Left is a reserved keyword in Vex code, so you can't use a variable with left in it. You'll get like issues. Okay, just don't do it. So name it something else. Now we'll name it left train. Left train is axis 3 plus axis 1. So forward. Sorry, I forgot mine. Forward plus sideways. Well, on the other hand, right train is axis 3 minus axis 1. So right train forward minus sideways. And bang, we have our two left and right values. So now we just need to plug in the left value to the left motors and the right value to the right motors. So we need to set the velocity for all of them. And if we need a reminder, this is how you do it. So we have our drive left front motor, set velocity. And the velocity we have is already calculated. We can just plug it in and remind the function we're using %, and bang, that's it. And we do this for all four motors. Drive, left. And we just do this for the right side as well. And you remember to change out the right side for the right numbers. Okay, well, we set the velocity, but we haven't told any of the motors to spin, so nothing will happen. So So we need to spin them all. Drive, spin, and you can just leave it as forward, because anytime we're going backwards, right, if you remember our test cases, this number will go negative. So it's already accounted for by going negative in here. So you can always just leave this forward. Let's do this 4 times. Quite tedious, but since this is a beginning tutorial, let's just do it this way. Alright. Well, will this work? Even though we implemented our algorithm correctly, there is one issue, which is that when we run this code, it only runs one time, which means it will take a snapshot of whatever state your controller was in, and it will stay that way forever. It won't update with your controller, because you only ran it one time. So how can we solve this? Can just keep this in a forever loop, right? So let's just keep it in a while true loop. Bang. And this will keep repeating forever now. Alright, so one last thing. If you explore the tab here, you'll see set stopping, right? So what is that set stopping? It's also a thing in FLL. You have 3 different stopping behaviors, right? You have brake, coast, and hold. So let me explain kind of. Brake, it will actively, like, the motor will actively, if you were turning forward and then you stop, the motor will actively turn backwards, kind of, to kind of like counter your forward momentum so that it comes to a stop immediately. Okay. The benefit of this is that, well, you stop very quickly, but the problem is that this braking action takes quite a bit of energy, and your motors will burn out a lot quicker, like get hot and like run out of energy. Coast is when you spin it forward, you tend to stop, you just let the momentum keep going. Like, it won't supply more power, but it won't like actively try and counter that forward momentum. It will just let it slowly come to a stop. So the benefit of this is that it saves a lot of power, okay? And yeah, it just saves power, you won't burn out as quickly. Some people don't like to drive like this, but some people do. So you should try both and see what your driver prefers. Hold is that when you move it forward and then you tell it to stop, it will keep trying to maintain that encoder position. So if you move it forward, you stop it, then you push the robot forward, the robot will just move back to where it stopped at originally, like automatically, without you having to code anything. So this is pretty good for autonomous mode, but honestly it's like really overkill for drivers. So we probably want to set this whatever you want. I think the default is brake, but if you want to change it to like coast, you can just repeat this, right? Not in the while true loop, because you only need to set it once. So you can do it like out here, and instead of spin, you just set stopping, and maybe I want to coast. So let me just paste everything. Bang. Okay, at the start of the code, as we're initializing my driver control, I will just set the stopping. Yeah. Apologize for that. Yeah, so that's how you set your motors. That's really all you need to know. Yeah, so honestly, if you want to stop here and just test your bot, this is perfectly fine code. If it doesn't work, please go and find a senior. I haven't tested this, but it should work. But yeah, if you want to stop here, you absolutely can. This should work. But I'm gonna continue and fix some nitpicky issues with the code design here to have a more readable and maintainable code lah. Okay, but you can stop here if you want. Yeah. Okay. Well, one issue here is that, say we don't want to use the driver code anymore. We want to write some autonomous code, right? Every time we do that, we have to like comment all this out. What is the Python? Oh yeah. Comment all this out and write out code here. Like, that's a lot of work. So instead of that, perhaps we can put all this into one function. Maybe we call it, let's just indent it. We can put all of it into a function. Let's call it driver control. I forgot about the set stopping, so you can just put it in the function too. So just here, so when you call driver control, it only runs this once, then you go into your loop. Yeah. you can just put it in front here. Okay, so now when we need it, once we coded the control, we can just put it out of sight and out of mind because we don't need to look back at it anymore, right? And when we need to run the driver control, we can just call it anyway, driver control, and it will run the code. Oh, driver. Yeah, so it's a lot neater, more maintainable. And if you don't want the driver code, you want to run like your Auton code, right? Like you have to code this yourself, obviously. Like there's no Auton code function. Imagine you coded this. You can just comment this out, and this will run instead. So yeah, you should probably group your functions like that. Like driver code, maybe you have Auton 1 and Auton 2. You know, you can just put that in functions and you can choose which one to run. It's a lot easier like this. Yeah. Okay, well, let's continue looking at our function here. Well, we can see like a lot of it's repeated. It's very very tedious. We have 4 command lines here, 4 lines here, and it's all kind of doing the same thing. And if we ever want to code like Auton, say even a very simple thing like moving forward, right, we have to call 8 lines just to move forward. That's kind of crazy. So instead of that, a good practice I like to recommend is to put all this into like a function that you only need to call one time to do these 4 lines. Okay, so what I mean by that is we can have I always call it drive macro. So define drive macro. I have a parameters like action and value 1, value 2. So keep it general because this action could be anything. We don't really know what this value represents, right? So and we probably want to create some actions to do here. So if you look at this, some good actions would probably be set, velocity, and spin. So maybe higher up here, we have like variable like declarations, and we can set some actions. We can have set speed equals to 0. This number is arbitrary. It's just so that I can write like if action equals to set speed. It's a lot more readable than if action equals to 0. And I'm supposed to remember that 0 means set speed. So by doing this, you can have like enums for your easy reference. So set speed, and maybe you have spin equals to 1, and you want should rename it something else because spin is a keyword. So start spin, I don't know, you can recreate it. Start spin. Obviously you want these two to be different numbers so that the compiler can tell that like, they're supposed to be different. Well, if action equals to set speed, sorry, I'm not following what I preach. Please keep your naming consistent. Yeah, okay, so say if action equals to set speed, we'll set all 4 speeds here, and then if action equals to start spin, can split. Oops, split. So like you have this, right? Let me just copy it. And if you have set speed, value 1 can equal like left train. Value 2 can equal right train. So you can be creative with like what this represents, but you just have to write it down somewhere for your team members or whoever's maintaining the code to like say to know. Okay. Train. So instead of left train, which isn't defined here, you just replace it with appropriate parameter. Value 1, value 1, value 2. So instead of calling all this all the time now, you can just call drive macro set speed, and you have left train, train, right train. Yeah, and we condense 4 lines into 1 line. Okay, in this situation, it looks like we're writing a lot more just to reduce 1 line. But if you really think about it, when you're writing Auton, you're gonna be setting speed so many times. Do you really want to repeat 4 lines just so when you have a function like this, you can just condense it down. So let me just finish. Let's cut. We spin everything. Very simple, very easy. So here's our little drive macro. Okay, we can drive macro, set speed, drive macro, spin. Start, spin. And since we're not really using these values, we can set them as whatever. So I'll just give them trash values. Yeah, so you see, so much cleaner, so much more condensed. Yeah, and it's just more maintainable code lah. Especially when you start writing Auton. Like all these practices is for you to make it as easy as possible to write Auton. Yeah, well, this is about it. All you can do for your drivetrain. Maybe the next steps from here is to code your intake if you're done with that and other stuff. And if you do join Vex, this is not it. There's a lot more. A big part of Vex is autonomous mode, where you code to move the robot autonomously within your first period of the match. So that's a big part of what you can do as well. Because the board is so big, you have to use sensors, mostly encoders and your gyro to maintain a very accurate position. So it's quite interesting, and you can look forward to doing that if you try Vex. So that's it. Bye bye.